Yeah, everybody can hear me, right? Okay. So good morning. Good morning, everyone. I heard you had a very good week last week of lectures. I hope will not disappoint you this time. So I prepared 3 lectures on strongly correlated distorted systems. It's a long journey. I've written up some notes that you can find here. So I'm not sure I prepared too much stuff, so if there's stuff that I won't be able to talk here, they are there in the notes. So some instructions, if you find any errors in the notes, please let me know. I've just written them up, so it's very probable that there are errors there. And also, please interrupt me. If you have any questions, anytime, just raise your hands and ask the question, okay? Okay, so let's start. So, according to the title, I will be talking about disordered, strongly correlated systems. So trying to prepare the lectures, I realized that I have to first tell you about correlated systems, strongly correlated systems, the clean version, okay? So probably today, there will be no disorder, just strong correlations, because I have to prepare the groundwork for you to understand what comes next, okay? And I hope it's not too boring. So, okay. So just a quick introduction. Everybody learns in undergraduate physics about solid-state physics, band structure calculations, and such stuff. And there was a huge success in the quantum theory of solids, in the calculation of band structure of solids. We have learned a lot about the behavior of solids from these calculations. We learned how to distinguish insulators from metals, from semiconductors and other stuff. However, there are a lot of other materials which cannot be well described within the usual band structure theory, and these are materials we call strongly correlated materials. So there are many examples of these materials. I think we should start first by talking about magnetism, magnetic systems, ferromagnetic systems, antiferromagnetic systems, and others. They require a special dedicated treatment of electronic interactions. So these are perhaps the first examples of strongly correlated systems, but there are others also. Most famously, perhaps in the last 30 years, the high-temperature superconductors have been very well studied, and they are a prime example of strongly correlated systems. So I'm going to give you my perspective on these systems, which is not necessarily the only one. And I hope you can appreciate what I'm going to tell you. So as in any area of strongly correlated systems, we usually work with effective models, okay? So I'm going to, in this lecture today, I'm going to talk about some effective models that are very important for the development of this area. And so let me start by talking about the Hubbard model, which you probably know about. So the Hubbard model is a model of one band of electrons with spin a half. So this is a hopping term. If you want to say, you can say that it's a kinetic energy term, plus a local interaction between the electrons, so-called Hubbard interactions. Okay? So this is a free fermionic model. This is an interaction term. This is what makes the model hard to understand. So this model has been used to address an important problem in this area, which is the MOT, metal insulator transition, which is a metal insulator transition driven by interactions. Okay? So let's talk about a few limits of this model. The non-interacting limit is very easy because you can, by doing a Fourier transform, okay, I'm going to go over a few steps here, which I think are perhaps a bit too trivial, but if you don't understand, please interrupt and ask questions. So if you do just a Fourier transform of this system, let's put a 0 here for no interactions, you can write this system in the K basis, crystalline momentum basis, and then it's a diagonal system in this basis where epsilon of K is the dispersion. So in a cubic lattice, it's going to be something like this. Okay? So this is a free fermionic system. You can, the ground state of the system, you fill up all the states from the lowest energy one to the largest necessary to fill up with all the electrons you want to have in the system, always putting one up and one down electron in each K state. And you have a metal, usually. So, because here's the Hubbard model. This is a picture of the Hubbard model. So as I said, the first term describes a non-interacting band. If you fill it up with a number of electrons, which is not 0 or 2 times the number of sites, you have a metal. Okay, so pictorially, you have a Fermi surface like this one. So for the 2-dimensional case, just cosine kx, cosine ky, you fill up this square of the Brillouin zone, and you have a metal. Why do you have a metal? Because you can make arbitrarily small energy excitations by creating particle-hole pairs. Okay, so if you have somehow the Fermi surface like this, you take an electron here, put it there. This is a low-lying excitations because you can do this very close to the Fermi surface. And if you now apply a small magnetic field, small electric field, you're going to create a current that's going to go through your sample. This is going to be a metal, okay? In real life, there are always impurities that are going to give you a finite resistivity for this system, but it's going to be a metal, a good metal. So this is the easy version of the model. Now we can do the other part, which is t equal to 0, where you have only the interaction term. And this term is already diagonal in the site basis. So the first term is diagonal in the K basis, the momentum basis. This is diagonal in the site basis. So I don't know if I prepared something here. No, it's this way here. So if you have t equal to 0, the electrons cannot hop from one side to the other. You put one electron on each side with the spin up or down, okay? And you have an insulator because they cannot hop, especially if you have what we call half filling, which is 1 electron per site. This electron cannot move because the electrons cannot move because for them to move, you have to transfer it to the neighboring site and create a double occupancy site, and that pays an energy U, which is very large, or is the only energy in this limit, okay? And so the electrons will not move with a small electric field. This is an insulator. This is what is called a Mott insulator, okay? Because if you put 1 electron per site in this limit, you just fill this square, this red square here, you have a metal. But if you have 1 electron per site here, this is an insulator for the reasons I gave you, okay? Okay? Can I go on? All right. Now, of course, in this limit here, you have a very large degeneracy for the ground state. If you have for each site where there is an electron, the spin can be up or down, okay? And if you're in this limit where you have 1 electron per site, and there are, so if you have now number of electrons, I'm going to call N, number of sites, I'm going to call NS. So this is what I call half filling. the degeneracy of the ground state is 2 to the n. Because for each site, I can put spin up or down. This is very large. It's an exponentially large degeneracy, okay? But it's the true ground state for half filling at t equal to 0. Now, it's important to ask now, what happens if t is very small, but not 0, okay? In that case, you can lift the spin degeneracy that you have here, okay? And you're going to have, the charge dynamics is frozen. The charge cannot move from one side to the next one because U is too large. You pay, at least in low energies, right? At low energies, you pay too much energy to move an electron to the nearest neighbor side. So you only have spin dynamics. Now, if U is very large and T is small, the spin dynamics can be well described if you do perturbation theory. So if T is less than U, I can do perturbation theory in T over U and ask what is going to be the spin dynamics of this system, okay? So now, I'm not going to do perturbation theory for you here by doing real calculations, but I'm going to argue that it's very easy to know what's going to happen in this case. One election per site, yeah. Number of elections per site.
Wouldn't it be full filling?
Yes, so you can have at maximum, the number of electrons can be at most 2 times the number of sites because it can be up or down. Okay, so half of that, half filling. All right? Okay. So if you now, where was I? Here. Okay, so if you want to do perturbation theory, have to go to second order. First order is 0. And I guess you all remember the expression for second order perturbation theory, except that here is degenerate second order perturbation theory, which is usually not discussed too much, but it's not too hard. The formula is basically the same, except that the states alpha and beta are any states in the manifold of spin configurations that you have here. Okay, so alpha and beta are any of the 2 to the n states that I wrote here. Okay? Now, the physics of the spin dynamics is very easy. Okay? Suppose you are in the situation depicted here. So you have 2 neighboring sites, and they are both aligned, either up, up, or down, down. Okay, so perturbation in T is going to do what? It's going to transfer the electron to the neighboring site, and because it's second order and you have to go back to the ground state, you just go once and come back, right? Okay? However, as you can see here, the hopping conserves the spin. So you can, if you are up, you can only hop up and then back. If you're down, you hop down. And you cannot do this here because Pauli prohibits this occupation of this site. So this is forbidden. The other one over there is possible. If they are like this, you can do this, and you have, for instance, that intermediate state there. Okay? This pays energy U. And then you can come back. But you can come back in 2 ways. Either you reproduce the initial configuration, or you exchange, you flip both spins, okay? And this will lower the energy by T squared, because it's twice the hopping term, divided by the difference between the energy of the ground state, which is 0, and the energy, the excited state energy, which is what U. And as you already know, second order perturbation theory always decreases the energy. So it's going to be minus T squared over U. Okay? So the physics is simple. This does not get renormalized to second order, but this gets lowered by a little bit of energy to second order. Okay? So in other words, second order perturbation theory does nothing to a ferromagnetic configuration spins, of neighboring spins, but it lowers the antiferromagnetic configuration of spins. So when you do this to the fullest, the Hamiltonian you get is the Heisenberg Hamiltonian. It's two spins, two neighboring spins interacting with the Heisenberg term, S dot S. Okay? And this J here is, if you do all the possibilities, which I did not do, is 4t squared over u. And J is positive. Okay? So J is positive, which means that you want to have spins like this. Okay? If you do the math, you'll see that this configuration gives you 0. This configuration gives you minus 4t squared over u. Okay? So in other words, the spin dynamics at low energies of the half-filled, strongly interacting Hubbard model is the Heisenberg model, the antiferromagnetic Heisenberg model. And you're going to see that most Mott insulators in nature are, at low temperatures, antiferromagnets. They order antiferromagnetically. And the explanation is this one. So it's very common for people to ask students this kind of question. So can you explain to me how, this is called superexchange, okay? This mechanism of lowering, of giving the spin dynamics is called superexchange. So if somebody asks you, can you please explain to me superexchange? You just do this with pictures, okay? Good. So I covered already now the Hubbard model and the Heisenberg model. But there's one thing I didn't mention about the Hubbard model, I forgot to mention, which is the following. So I'm at half filling, and here I have a metal, here I have an insulator in the two limits, okay? So I expect that there is a U, so this model is governed by the ratio of the two energy scales U and T, right? So I expect that if you vary that ratio from 0 to infinity, there's going to be a phase transition between from a metal to an insulator, okay? And that's what happens when this guy reaches a critical value. You have a so-called Mott or Mott-Hubbard metal insulator transition driven completely by interactions, okay? And the Mott insulator, we learned at low temperatures, is very probably an antiferromagnet. So we are learning some new physics here, I hope. Okay? Good. Any questions at this point? All right. So the next model I'm going to talk about, I think I have a slide here. Oh, no, I have a few, I'm sorry, I forgot about this. I have a few experimental data on some Mott insulators, which are the following. So in nature, there are metals for which U over T, if the Hubbard model is a good description, is very small. There are Mott insulators where U over T is very large. But then there are systems which are very close to the critical value of U over T. And these systems you can tweak a little bit, and you can go through the transition by, let's say, it's very common practice to put external pressure. Okay, so pressure usually will, so if you put pressure, if you increase pressure, you will decrease T, because T depends on the distance between the atoms. Okay, so if you put a lot of pressure, T is going to be smaller, so U over T is going to go up. Okay? Because T goes down. I'm sorry, I exchanged stuff here. I'm sorry. So if you put pressure, the atoms will get together, and it's going to be easier to hop from one side to the other. So T is decreasing, and U over T is increasing, U over T is decreasing. Okay, so you tend to metallize a Mott insulator if you put pressure. Okay, and this is what's seen here. Well, first of all, this is the phase diagram of a very famous system, V2O3, vanadium to oxygen 3, which has this phase diagram. You see there's an insulating phase. Let's look at high temperatures, 300 Kelvin, for instance. You have an insulating phase, you have a metallic phase that you can reach through pressure by that mechanism. At lower temperatures, you have an antiferromagnetic insulator, as expected, okay? Now, the Mott transition proper is what happens at that transition line there. Okay, that transition is a first-order transition, which means that, for instance, the usual way of characterizing metallic or insulating behavior is looking at the conductivity or resistivity, okay? So what happens is that as you cross that line, the conductivity or the resistivity has a jump, characteristic of a second-order phase transition. But as you see over there, it ends at a critical point. So this jump, as you go along that line, gets smaller, 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 and at the critical point, the jump is 0. This is very much like the liquid-gas transition that we know, okay? So this is a more recent paper. This is the jump in conductivity as a function of pressure for different temperatures. You see a big jump. There is hysteresis also, okay, characteristic of first-order transitions. It goes in one way. If you go in one direction, it goes down one way, and if you go back, it goes up at a different point. And as you can see, the jump gets smaller, 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 and at some point it becomes 0. That's the critical point, okay? I think that's it. All right. Okay. Any question here? Yes, please.
Can you come back one slide, please? So yeah, I have 2 questions here. I see that you are in very low temperature when you become, if I fix in pressure, you become an insulator at very small temperature, let's say, compared to the room temperature. But what about pressure? This is like in the y-axis, the x-axis. This is like this is like atmospheric pressure. How can I compare with the normal pressure that we are using?
Well, you can see here, right? It's not very large, kilobar.
Kilobar.
Kilobar is okay. Most labs can do that.
Okay, so but it's very high pressure compared to what to.
Oh yeah, this, if you put this kind of pressure, you're going to make the atoms just a little bit closer.
Okay.
Which is why it's very hard to tune the transition in other materials, other multi-insulators, because they're so far that you just tune a little bit. And so this is a special material because it turns out to be on the brink of the transition, and a little bit of pressure, and I'm calling this a little bit of pressure.
So it's hard
can metallize.
It's hard to do this, or
4 kilobar is not too hard.
Okay. And what about the lines? Is this line predicted by the model that we were?
I'm going to talk about later about that. Okay. Okay. So let's move on. The other model I have to tell you about is the so-called single impurity Anderson model. Okay. This model historically it tried to address the following physical question: you have a good metal, let's say copper, and you put a little bit of iron, few impurity ions of iron, or manganese, or any ion that's in vacuum magnetic, in the sense that it has an open shell with a magnetic moment. The question is, if you grow a copper sample with a few impurities of iron, will the impurities keep their magnetic moment when they are in the metal? It's a non-trivial problem for the reasons I'm going to give you here, okay? So this is the model. You have one band, free band, one impurity with energy epsilon d, a so-called hybridization term that can move the electron from the d impurity to the band and vice versa. And you have interaction in the impurity site, okay? Now let's turn off the interactions and look at this part of the Hamiltonian. This is also a free Hamiltonian. It can be solved exactly. Now, the physics of this Hamiltonian is the physics of a resonance. Okay, so what happens is the following. If V is equal to 0, you have a state, an impurity state at epsilon d and a band of electrons. Let's assume that the band is filled up to this point here. Now, because of the hybridization term, the impurity level will mix with the band and will delocalize. Okay? And this will be effectively described by a resonance. Okay? So I think I have a few. So if I calculate, let's do it here, the so-called density of states of the D site, it's going to be given by what we call a Lorentzian, okay, centered at the energy of the site with a certain width, gamma, which is given by pi rho. This is the conduction electron density of states calculated at the impurity site times v squared. Okay? So this is a Lorentzian resonance that's describing the fact that that guy is there mixing with the conduction band. Now, if you fill up with electrons according to the Paulo exclusion principle, you're never going to be magnetic. Because for every state in that hybridized band, you can put the electron down and electron up. Okay? And in the thermodynamic limit, it's never going to be a localized magnetic moment at this site here. For instance, if you fill it up to the to half, it's going to be half filled sites of this resonance with electrons up and down, up and down, up and down. It's not going to be magnetic. So in the absence of interactions, you get this resonance, and you get no magnetism. So the magnetic moment was dissolved in the metallic band. Okay? So you lose magnetism. Now take the other limit. Take V equal to 0. If V is equal to 0, you decouple the band from the impurity. So the band is here. Okay? And the impurity is over there. And you have those configurations. You can have 0, so ND equal to 0 with energy 0. You can have one electron up or down. So this is OR, okay? This is just one electron. This is ND equal to 1. And let's assume that epsilon D is negative. So this is going to be lowered by this amount. So, okay, so this absolute value of epsilon D. And if you put both electrons on that site, you're going to have to, the energy here is going to be 2 epsilon D plus U. So this difference here is epsilon D plus U. Okay? So if this is true and epsilon D plus U is positive, this is the configuration you have for that site. So the lowest energy configuration has one electron in the site, and it's either up or down. This is what I call a magnetic moment. So if you are in that situation, and if you measure the magnetic susceptibility, you get a Curie susceptibility, 1 over T. Okay, if you have many impurities in the dilute limit, it's going to be the number of impurities times 1 over T. So this is a Curie susceptibility. This is the number of impurities. This is a local moment. This is a local magnetic moment. So those are the two limits that are easy. In this limit here, I have no magnetism, no magnetic moment, because you always compensate a spin down with a spin up. In that limit there, with that choice of parameters there, I have a magnetic state. Now the question is, if you turn on everybody, what happens? So the V term has a tendency to kill magnetism. The U term, together with the negative epsilon D, has a tendency to form magnetic moments. So there's going to be competition. Just like here, there was competition between kinetic energy and interactions. In that model, there's going to be a competition between local moment formation and local moment quenching or killing. Okay? So these two lines here, which are bounding the blue region, are the lines given by these two inequalities, or the two equalities. The blue region is the line between the two lines, is the region between the two lines. So in that blue region, if V is equal to 0, I have magnetic moment. Okay? Outside that green region, even at V equal to 0, I do not have a magnetic moment. Now, if you turn on U now, you can do a mean field theory. That's what Anderson did in his original paper. And you can show that the magnetic state still survives. It gets suppressed a little bit, but it survives in this yellow region in the middle here. This is for U V different from 0, and inside the yellow region. So inside this region, you have either the impurity site with 1 up electron and 0 down electrons, which is this, or you can have this. Okay? And this is going to give rise to a Curie susceptibility because this is local moment, even with interactions. So this calculation by Anderson showed, at least at the mean field level, that you can have, there is a condition for the magnetic moment to survive inside a metal. The condition is to be inside this yellow region. Okay? Is that clear? Can I go on? If not, please let me know. This is going to be important for what comes next. Okay, good. But see, we have 2 solutions. These 2 solutions are degenerate, again. This is a magnetic solution, two magnetic solutions which are degenerate. This is a mean field theory. These 2 solutions, they break a symmetry of the problem. You can take it to be the time reversal symmetry because spin is odd by time reversal. So if you have the state over there, and you apply time reversal, you get the state down here. And either of those solutions is clearly breaking that time reversal symmetry. But you cannot break any continuous. In this case, it's a discrete symmetry, but this is a 0-dimensional problem because it's just 1 impurity. You cannot break this symmetry at all. There are theorems that forbid this symmetry breaking to occur. So what we have to do is to restore fluctuations that go beyond the mean field theory to try to understand what happens in this system to these 2 solutions. So what fluctuations will do is that they will connect the 2 solutions. So the spin is like that. It's going to do this, it's going to do that, it's going to do this and that and this and that. And you can write down an effective dynamics for the spin doing perturbation theory, just like what we did for the Hubbard model. Okay, this is I just told you about. The perturbation theory here is very similar to this, but not the same, because now we have an impurity site with, let's say, spin up and the band. Now, to second order, you can take an electron here, bring it there. You have a double occupancy, and then you go back. You can go back with the same spin configuration, or you can flip the spin configuration. So you gain, once again, or you decrease the energy by a negative amount, which in this case is V squared, because each time you go to the band is a V term, is a hybridization term. And the difference in energy between ground state and excited state is double occupant state. It's this difference here. Okay? So in other words, you can do the same game that we did for the Heisenberg model, and you get this effective model here. You have the band, okay? And you have a term that comes from second-order perturbation theory, which is also a sort of exchange term, if you can call it like that, where S is the spin of the D impurity. So you have 3 spin operators there. And the electrons can, okay, this is wrong. One should be K, the other should be Q. So the electron can come with a certain momentum and be scattered with a different momentum, let's say Q. And as it scatters, it can flip the spin because there is a spin dynamics there. You can either not flip it or flip it. Both cases are there, okay? This is the Kondo problem. This is the so-called Kondo-Hamiltonian, okay? And this kind of scattering is sometimes called Kondo magnetic scattering, okay? Because you can't flip the spin. It's a very peculiar type of scattering. It's not trivial at all, okay? This is sometimes called the hydrogen atom of many-body physics. It's the simplest model you can write down that it's very hard to solve. Okay? It can be solved with Bethe ansatz, for those who know what that is, but that's not what we're going to worry about here. So the J term, the coupling term there, is very much like the Heisenberg term, except that in this case it's given, if you do all the processes at second order, which I did not do, you get a value for J, which is given by that. And if you are in this condition here, that J is positive. Okay, so it's also an antiferromagnetic coupling between the localized impurity and the conduction band. Okay? Yes?
Does this depend, the argument depends on dimensionality?
No.
Not at all?
No.
So it's valid for any D? And
Yeah. 1D is a little bit too trivial, right? Because you can have just forward scattering or back scattering. Except for that, yeah, it's the same. Yeah,
and what did you say that there were no possibility for symmetry breaking?
yeah, because it's just 1 degree of freedom, right?
Okay.
Which is the impurity spin, right? Yeah, just one more detail about your question. In fact, here, you can write, the model is actually, in a sense, always one-dimensional, in the sense that this is radial scattering. So the electron comes radially and goes out radially. So you can write it in the radial direction, and you have effectively just a 1D, let's say. That's how the model was solved with Bethe ansatz. Bethe ansatz requires 1 dimension. And the 1 dimension of the Bethe ansatz is actually the radial dimension of the scattering. Okay? Okay, so this is the Kondo model. It's a very rich problem, very rich physics, which I'm going to try to describe with words here. Okay? Which is the following. First of all, what is the ground state of this model? So remember, the ground state, according to the Anderson mean field theory, was either a spin up or a spin down. It's a magnetic state. Okay? Now, the ground state of the Kondo model is not a magnetic state. It's a singlet state. There's no spin. The spin is quenched or killed by the interaction with the conduction electrons. Okay, so it's screened by this so-called Kondo cloud. So it forms, the spin is the red thing in the middle. The blue arrows are the conduction electrons, and they form a singlet. This is a very complex, difficult to describe singlet, but it is a singlet. So in the ground state, the magnetic moment goes away because of Kondo screening. First thing to remember. Second thing to remember is that this problem has a characteristic energy scale or temperature scale given by this expression. This is the famous Kondo temperature. I'm going to tell you about it, but first let's look at it. This is the half bandwidth of the conduction band. This is the density of states of the conduction band at the Fermi level. So it's this, well, it's rho F, it's rho C at the Fermi level. And Jk is the coupling constant. So some things to notice about that expression. First of all, it's non-analytic in J. So this problem is not, does not lend itself to perturbation theory in J. This is what Kondo discovered in 1964. Before Kondo, people had already looked at this problem. They did perturbation theory to second order in J, and it was fine. The scattering was just like any other impurity scattering. There's nothing fancy about it. And what Kondo did is to go to the next order, and he showed that there is a singularity in the next term. So perturbation theory breaks down at third order and above. If you do it as a function of temperature, there's a certain temperature at which the perturbation theory breaks down. Okay? So at the time, this was called the Kondo problem because people didn't know what to do with it. Okay? And it's clear now that because the characteristic energy scale is non-analytic in JK, that perturbation theory has no hope of solving this problem. Okay? And there's a long history to the problem. I'm not going to go through it, but now we know that this is the scale that sets the difference between high energies and low energies in the problem. So if you are above TK, which is this region here, you do have a Curie behavior. This is a log scale on the x-axis, so you cannot see it, but this is essentially 1/T corrected by logs. As you go to low temperatures, however, this does not diverge, as the Curie law would say, but it saturates to a finite value. This is because you kill the magnetic moment. So if you kill the magnetic moment, you kill the Curie law, and you saturate at a constant value. And when that happens, when the change, or as we say, the crossover between high energy and low energy happens, it's at this temperature, characteristic temperature, Tk, or Kondo temperature. So remember this formula. We're going to come back to it later. Okay? Yes? I like questions because I can drink some water.
In this case, you say, when you decrease temperature, there is this screen effect that happens.
Yes.
But it comes from the fact that they are correlated, or what is the origin?
Yeah, this term, basically,
okay.
right?
That's what dominates in this
Yes.
regime.
Yes, yes. At high temperatures, they are decoupled. So it's like a free spin, which is Curie. As you lower the temperature, they start to interact strongly, strongly, strongly. And in this region here, it's extremely strongly interacting and forms a singlet. Okay. Good. This Tk is important because, as I said, it's the only energy scale that's relevant in the system. So any physical quantity can be written as a well-defined, so I have to use the other side. So this problem exhibits what we call scaling. And if you have a dimensionless quantity, in this problem, it's going to be given by a certain function where you have, let's say, T divided by Tk, okay? If you're doing some frequency-dependent stuff, you can put, forget about this, okay? I work with these units. Okay, so this is omega over Tk, and if you have a magnetic field also, if you put mu Bohr magneton here, this is also an energy, and everything scales with Tk. If it's a dimensionless quantity. If it's dimension full, it's going to be a prefactor that has the correct dimension, let's say, in dimensions of Tk, in powers of Tk. Okay? So this is an important fact about this problem. So this curve that I showed here shows that kind of behavior, right? So for the susceptibility, it's 1 over Tk times a function of T over Tk, which is what's shown there. The only scale that's important is Tk. This is a numerical calculation of the problem. Unfortunately, this is old stuff. This is by Ken Wilson. As you probably know, Ken Wilson discovered the renormalization group, and he applied it to the Kondo problem, and for both, he got the Nobel Prize. And there are a few papers about this with his name on it. And so this is the susceptibility now here, multiplied by T. Okay, so at low temperatures, it goes to 0 linearly in T, because the susceptibility goes to a constant, right? Why I show this, this plot is for the following reason. There is a region here where you have Curie law. This is a region where Anderson's mean field theory is good, okay? So if you go from very, very high temperatures down, there is a region here, this region here corresponds to the Curie law. So if you're measuring the sample in that region, you're going to say, oh, there's a magnetic moment here. It survived in the metal. But as you keep on cooling the system, the magnetic moment goes away. So people sometimes say that Anderson tried to show how magnetic moment can survive in the metal, but then if you look further, it actually gets killed eventually. Okay, but it's not useless, Anderson's theory, because there is an intermediate region of temperature where the magnetic moment is there. It may exist or not. In this case here, with a larger coupling constant, you go directly from high temperature to low temperature with no Curie behavior. Okay, this is what I wanted to show you. Okay, now I have to do some math, okay? Because I have to put a little bit of math in the description of the Kondo problem or the Anderson impurity problem. Okay, so I have to, you have to indulge me here a little bit. I'm going to define a few things, which are, I barely need, I need to do my stuff here. I wish I wouldn't have to do this because it's mathematics, and we like to give lectures which are only based on intuition, but unfortunately, I really can't go on without doing this part here. So now I'm going to define, so I'm back to the Anderson impurity model, which is not there, but I'm back to this problem here, okay? Where you have a conduction band and d impurity. And I'm going to define what I call a local green function for the d orbital, okay? So it's going to be a very strange thing, but bear with me. Where this is trace e to the minus bh Anderson over z at finite temperature, okay? So this is a statistical trace of this quantity here. This is the anti-commutator. And this is what's called a retarded Green's function for the d electrons, okay? It's retarded because this theta function makes the dependence on the difference. It's not obvious that this quantity here depends only on the difference t minus t prime, but it does, okay? It can be proved that this right-hand side only depends on the difference t minus t prime, okay? And so it's retarded because because of the theta function, t has to be greater than t prime. In other words, this guy here has a time. I forgot to say also that these are Heisenberg time-dependent. The time dependence of the operators come from the Heisenberg version of quantum mechanics, where operators acquire time dependence through these e to the IHT, e to the minus IHT factors, okay? Guess that's what I need. Okay, this quantity, I'm going to show you later, it can be measured in the lab. I'm going to show you some experiments. But it also represents the fundamental quantity for what I'm going to do coming Thursday. Okay, so I need to define it. And after I define it this way, I do its Fourier transform, where I just integrate over this difference. This is an eta. Okay, so I have to put this guy here because otherwise this does not converge. So this is from minus infinity to plus infinity. Because of the theta function, it's actually from 0 to infinity. But if I don't put this I eta, where eta is positive and small, this does not converge. Okay? So mostly we will be working with the frequency space version of this Green's function. And that's the function that's measured in the lab, actually the imaginary part of that function. This is, in general, a complex quantity, okay? So when you do that, you can define, so, okay, fine, any questions here? So I can take the imaginary part of this quantity. It's called the spectral function. I'm going to give it the same name as the density of states. Okay, so And this is what's plotted here, okay? This is for the so-called symmetric Anderson model. So the plot is for this so-called symmetric Anderson impurity model in which ED is minus 1 over U over 2. And obviously, ED plus U is U over 2. Okay? It's symmetric because this is minus this. It has a symmetry called particle hole symmetry, the problem has. Okay, so in this particular case, the spectral function is an even function of the frequency. And I plot here, or Yamada plotted here, the positive part of this function. And you can see, let's take this curve here. This is for various values of U. So, okay, let's start with U equal to 0.
Eduardo?
Yes, please, sorry.
Yeah, is that not just the density of states? What's the difference?
No, when you have interactions, it's a little bit different.
So in principle, this
in the non-interacting limit, it becomes the density of states.
Okay, okay.
Okay? It's almost the same thing. It's all right. So in the non-interacting limit, you get the kind of Lorentzian that I showed before. It's not actually centered at epsilon d, but it's centered at 0. Okay? But you have a Lorentzian, which is the dashed line that you have here. If you turn on interactions, it starts to get different. And if you put this large value of interaction here, you see that there is still a Lorentzian at low energies. And there's another peak at high energies. And if you calculate this peak here, it's actually at U over 2. Okay? If you put in numbers there, it corresponds to U over 2. So this peak here corresponds to transitions where in the ground state you have 1 electron. You're in that limit where you have this. Okay, in the ground state you have 1 electron. The spin of the electron is going up and down, up and down, up and down. At low temperatures forming a singlet. Okay? But if you go to high frequencies, you can so first of all, let me say this can be measured in experiments of the photoelectric effect. So you send in photons, you knock out an electron, so you destroy an electron in the system, and if you measure the energy of the electron coming out at all angles, you're essentially measuring this quantity here. You're measuring this quantity for negative omega, if you do what I said, but then there is also inverse photoemission, where you do the inverse, of course. You send in electrons, you collect photons. Then you get this quantity for positive omega. So this is called inverse photoemission. So this graph here can be, I'm going to show you some measurements of this kind of thing. So this is what you get for inverse photoemission. For photoemission, get the other side, which as I said, is an even function. For this case, symmetric case. Okay? So this peak here corresponds to a transition from n equals 1 to n equals 2 in the impurity. So you impinge an electron, the electron goes into the impurity, and you double occupy the impurity, so you go to Nd equals to 2. And the energy for this transition is this energy here, which in this symmetric case is 1 over U over 2, which is why this peak happens at U over 2. Okay? So this peak is easy. There is a corresponding peak on the other side, on the negative side at ED, which for the symmetric case is minus U over 2. It's a symmetric curve. But the interesting thing is the peak at 0 frequency, the peak in the middle. So this peak is called the Kondo peak. It corresponds to transitions where you do not change the occupation of the D level, but you probe the spin dynamics of the D level. Okay? And you can see that for very large U, it's very narrow. Okay? Actually, you can show that the width of this peak is the Kondo temperature. Okay? So this is the expression of the condo temperature in the symmetric case. If you go back to the J, let's see. Use this J for the symmetric case, put this J into this formula, you get this. Okay? And this is the condo temperature for this problem, for the symmetric Anderson model, and it gives the width of the so-called condo resonance, condo peak, which is this low energy peak of the model. Now, as I said, this is this, and this quantity you can show can be written as, or better, let me use that part over there. Once again, more math, it's needed, cannot avoid it. You can write the Green's function as 1 over omega minus epsilon d minus delta of omega minus sigma of omega. Now, delta of omega is easy. This is the so-called hybridization function. And it can be obtained from the band, from the V term in the Anderson model, the dispersion of the band, and you have to put in this eta, small eta, the same eta that I had here. Okay, so this is the hybridization function. Okay, it has real and imaginary part. Usually the real part is very small, especially for the symmetric case. What's important is the imaginary part of this function. But this is easy, okay? This comes from the model. This guy here is different. This is the so-called self-energy. This comes from interactions. So if U is equal to 0, no self-energy. You only have this. And if you take the imaginary part of this guy, you get that same Lorentzian that I showed there at 0. Okay? Where this gamma here, in that case, so it's Lorentzian centered at omega equal to 0, with width equals to imaginary part of this hybridization function divided by pi. Usually it's a minus sign. But if you have interactions, self-energy is not 0, and it's going to modify this picture. So for instance, if you want to calculate for U equal to 5 pi times delta, you have to put this in. This comes from interactions. Okay? That's the hard part of the problem. Okay? This is what's hard to calculate. So this is going to play a very important part in what I'm going to tell you about next time. But let me tell you the following. This is hard, but it can be done. Okay? There are several methods with which you can calculate, for instance, this Green's function, take the Fourier transform, equate it to this, and get the self-energy. Okay? Or you calculate directly in frequency space, and you get this omega here. So for instance, this plot here was obtained as a perturbation theory in U. In U, not in JK. It's different. There is no good perturbation theory in JK, but there is good perturbation theory in U. And if you look at the Kondo temperature expression, the U is above. So U has a very nice, well-behaved perturbation expansion in U, although it does not have a good perturbation expansion in V. Okay? So this was calculated with, I think, fourth order perturbation theory. Okay? And then you can calculate this guy, the self-energy. And if you do that, you get this picture with a narrow Kondo resonance at 0 and a broad peak at U over 2, at high energies. Okay? Okay, so if I want to calculate the Green's function, spectral function, and so on, I can go to my computer, or I can do U perturbation theory or whatever. I can calculate this guy or this guy, and then get the self-energy or the imaginary part of the Green's function, where here, and you get this plot over here. Okay? So this can be done. Okay? It would be a different mini course to tell you how to calculate this, but it can be done. So let's assume that there is a black box. You say, you give the hybridization function, you give the value of U, the black box spits out the self-energy somehow, okay? And then you get this. Okay, good. But you're going to say, well, but this is just numerics. I want to get a better handle of the physics. And usually we're interested in low energies. Well, not always, but usually we're interested in low energies. And there's one way you can not solve, but parameterize the low frequency, low temperature behavior of this problem. This is what I'm going to tell you about now. It's probably going to be the last part of my talk.
A quick question, Eduardo.
It's a good point for questions.
Yeah. I cannot help but notice there seems to be some similarities between those expressions and expressions for gaps in superconductors. Is there a parallel there?
No.
Condo temperature.
No. Well, only in that sense, that the critical temperature in BCS theory is also non-perturbative. There is something in the denominator inside the exponential. But that's the only, the only common thing between this and superconductivity. Superconductivity is another problem that's non-perturbative, at least in BCS.
So this might be a somewhat basic question about perturbation theory, but so you said that second-order perturbation theory always lowers the energy, but the sign of your energy depended on the sign of U. So what happens for negative U?
Okay.
And of course, if there's some sort of singularity at U equals 0, why does perturbation theory in U work?
Many good questions. Okay, let me start with the first one, okay? So the negative U problem is also a problem. It's less studied, but it has been studied. What happens there is that you flip charge and spin. Okay, I'm not going to explain everything, but basically, charge can be 0, 1, or 2, right? Which was here, right? So you can think of 0 and 2 as spin up and spin down in charge, okay? And n equals to 1 is spin 0. Okay, so if you take the negative U model, you flip spin and charge. So everything I said about the spin becomes a description of the charge dynamics. There have been some interesting ideas floating around the negative U problem. There are even some materials where it makes sense to talk about infinite negative U, where 0 and 2 are more stable than 1. I can tell you why. If you have atoms and you close a shell, that's very stable energetically. Okay, so if you go from a closed shell minus 2 to a closed shell, these two guys are very stable configurations, and the n-1 is not. So there are some ideas of trying to apply negative U to that problem. Okay, now here, let me see. Not sure I know the answer, but I think what happens is that the other question you asked, which is excellent question. You know, I'm going to be completely honest. I'm not sure about the answer to your question. I have a hunch, which is that this was in the symmetric problem. It turns out that perturbation theory in this problem for the asymmetric Anderson model is very hard. Actually, nobody knows how to do it. It's sort of amazing. And I think it's probably connected to that. Okay, so, but I have the feeling that one thing is for certain. If you just change the sign of U, you exchange spin and charge. Okay, so you probably get the Green's function does not distinguish charge dynamics, at least not per se, charge and spin dynamics. It has both in it. But I think that in the negative U case, you would get an absolute value there. I'm not completely sure, okay? But it's a good question.
Thank you.
It's a very good question, which I don't know the answer to, for sure. Other questions? So the last part of my talk, I'm going to try to show you an effective description for the low-frequency behavior, which is the Kondo resonance in this problem. Okay, so I'm going to ignore this physics here. I'm going to just focus on the low-frequency behavior. Okay, so I have to start here. So what I'm going to tell you about is Fermi liquid theory. So Fermi liquid theory is usually connected to the name of Landau. You probably heard about this. This is actually at least half of the Nobel Prize that Landau got. The other half was for bosonic theories, bosonic systems. So this is for fermionic systems. Landau is a sort of a plague in this area because this is basically a phenomenological theory. It has a certain microscopic derivation, and I put it between quotation marks because it's not really rigorous. You assume a lot of things along the way, and if those things work, then you can prove Fermi liquid theory microscopically. But this is a theory of fermionic systems at low temperatures in its original form with short-range interactions, but you can't put Coulomb interactions with a small modification of that theory. So it was originally proposed by Landau to describe the isotope 3 of helium, so-called helium-3, where the nucleus has 2 protons and 1 neutron. So the atom of, it's not the most common isotope of helium. The most common one is helium-4, 2 protons, 2 neutrons. But it is a stable isotope. You can separate it. And it turns out that helium-3 is a fermion. So at low temperatures, as you probably know also, at ambient pressure, helium is the only material that remains liquid down to 0 temperature. All the other materials solidify at a certain temperature as you cool them. But helium doesn't, at least at ambient pressure. If you put a little bit of pressure, not too much, it does solidify too. Okay, but at 1 atmosphere, you can cool it down to the lowest possible temperature, it remains a liquid. So this is a description of this liquid phase. This low, actually it's not also true because helium-3 becomes a superfluid at very, very, very low temperatures, below 2 milli-K. But between 3 milli-K and 3K, this theory applies. And it's due to Landau. So it can explain part of the behavior of helium-3. It can also explain the behavior of metals, modified for Coulomb interactions, but it can explain the metals. And it's very hard to avoid Fermi liquid theory. Actually, people have been trying for many, many, many years to find ways of breaking it down. It's very hard, okay? We would like to do that because there are a lot of systems that suggest that Fermi liquid theory is not working, but it's extremely hard. So originally, this was proposed for helium-3, it was used for metals, it is still used for many metals, okay? But here, in this part of the talk, I'm going to tell you about Fermi liquid theory for the impurity level, okay? It turns out that it can be applied also to the impurity of this problem. It's a fermionic system, so that's a start. But it can also be applied there, okay? First person that did this was Nozière. Not the way I'm going to tell you about, but he proposed this so-called Fermi liquid theory description of low temperatures for the Kondo or Anderson problem. Okay? But I'm going to do it here. So Fermi-Liquid theory does the following. So as I said, the hard part is the self-energy. I don't know how to do this, right? I don't know how to treat this. This is hard. So at low T or omega, okay, there is a sort of a good description of the self-energy, which is given. Essentially, what I'm going to do is to expand this as a Taylor expansion in these small quantities, okay? But Fermi-Liquid theory is going to tell me something more about this. So it's going to be a small real part plus, actually, minus A omega, okay? Plus an imaginary part, which I called, I think, gamma again. Yeah, unfortunately, I used gamma again. Shouldn't do that, but anyway. Where this guy goes either as there are some coefficients here, so I'm going to put B here and B prime here. So this is for omega greater than T, this is for T greater than omega. So in other words, whichever one is bigger, the imaginary part goes as the square of that quantity. Okay, so what Fermi-Liquid theory tells us first is that if you expand this guy, the constant term is 0, number one. Number two, the linear term is 0, and it starts at second order in omega or T. Okay, so this is Fermi-Liquid theory. The real part can have more terms, okay? So if you have a good theory for the self-energy, it's going to give you the value of these parameters, delta A, B, and B prime, okay? So I'm not going to tell you how to calculate them. I'm going to assume that they are there. Okay, so if I do that now, I can put this back into the Green's function, and it goes like this. Epsilon D, okay, minus this guy, which I'm going to also expand. Actually, sorry, plus. So I'm going to expand this guy here. Real part at 0 minus I, imaginary part at 0. So when I put it back there, because it's minus delta, it's plus, plus. And minus, it's too long here. Minus delta, plus, no, minus delta, doesn't matter actually. Minus delta plus A omega. Let me, for a moment, just, well, let me put it there. Plus I gamma. Sorry for the big expression, okay? Now, I can work with that, okay? For the following reason. I can write this way. See that this is also linear in frequency, so this becomes 1 plus A omega minus epsilon D plus, no, minus, plus the real part minus delta. So, yeah. So this is just the frequency part, the linear part. This is the constant real part. And then I have plus I delta plus gamma. Okay? Now I'm going to do the following. I'm going to divide numerator and denominator by 1 plus A. So this is going to become 1 over 1 plus A divided by omega. There is this part here. I really don't want to write this stuff because it's going to go away very soon, but I have to do it. Plus divided by 1 plus A plus I delta plus gamma divided by 1 plus A. Now, I have to continue somewhere else. Let me start here. I'm going to call 1 over 1 plus A, I'm going to call it Z. And anything that's multiplied by Z, I'm going to put a tilde. So for instance, delta Z is delta tilde. This is imaginary. Sorry. So Z times gamma is gamma tilde. Everything that is multiplied by Z, I call it tilde. If I do this, G of D, GD of omega becomes Z over omega minus, once again, that stuff, plus that stuff, plus minus delta tilde, plus I, no, just one tilde. And this is the final form that I want, okay? Why? Because first, for the Kondo-Anderson impurity, the following facts apply. This comes either from doing perturbation theory or from doing numerics or any other way you solve the problem. Okay, first of all, number one, E minus plus is approximately 0, which is why I didn't want to write it, because it's going to go away, because this guy is very close to 0. Because these two, this is epsilon D, these two come from the Hamiltonian. This comes from the self-energy. So what I'm saying is that the real part of the self-energy at 0 frequency adjusts itself to make this 0. When it does that, the resonance falls at 0. Because if I take the imaginary part of this, okay, so next thing, right? Minus 1 over pi, imaginary part of this is going to be Z times divided by omega squared plus Z squared, which is a Lorentzian. So, okay, so this describes this low energy part here. It's centered at 0. It's centered at 0 because of this. Okay? And the width of the Lorentzian is given by this. So this is the third thing. Is that the width is, I'm sorry, I put Z's, the Z is here, but this Z is not there because it's already multiplying. Here it's correct now. It's correct now. The Z is here because it's in the numerator. The Z is inside these guys because of the tilde, but I can't put Z again here, right? So that's it. So the width of the resonance is this stuff. This is the width. And at 0 temperature, this goes away, and I have this, which is Z times the imaginary part of this guy at 0. And remember, this is Tk, right? I said that this is Tk. The width of the resonance is Tk. So Tk is very much connected to Z. This is from the model, right? This is, if I take the imaginary part of this guy here, real part plus imaginary part minus, okay? So this guy is that guy. So the effect of interaction is just contained within Z. Z has many names. It can be the quasi-particle weight. It can be called the wave function renormalization, depends on the context. And it also gives you, when multiplied by the bare hybridization, the Kondo temperature. What else do I get from Fermi liquid? At 0, so this is number 4. Rho d at 0. So this is rho d, right? Rho d at 0 is Z times this divided by squared. This is Z divided by this guy. And at 0 temperature, this is Z divided by this guy, which is Z times this, right? Because it has a tilde. So it's this, so you cancel. This is not renormalized. Okay? This is the original hybridization. This is calculated with finite U. Okay? But at 0, it's not renormalized. And as you can see there, it's always the same. The height of the Kondo resonance is pinned at 0 temperature to the non-interacting value. Never changes with U. So this is also contained within Fermi liquid theory. And finally, the weight, which is rho d of omega, integrated, is Z times, it's Z. I'm not going to do the calculation, but it's Z times. Tilde, which at 0 temperature becomes Z. Forget about the Z here. No. Yeah, it's incorrect. It's incorrect. Let me remember from my notes. It's just Z. Forget about this, just Z. Yeah, because if you integrate it, this is actually, it's correct. No. There's a pi here. Okay, if you divide it by pi, integrate the Lorentz, you get pi. And everything goes away upon integration, you're left with Z. Okay, so this weight here is non-dimensional, and it's given by Z. Okay? So in other words, I think I wrote this down somewhere here. From Fermi, well, first of all, let me show you photo emission and inverse photo emission measurements on some cerium-based systems. The cerium is the magnetic ion. Okay, so let's start with this one. You have a peak here, which is minus epsilon d, a peak here, which is epsilon d plus u, and you have a Kondo resonance in the middle, right? You have to put the two together there because one measures negative of frequency, the other measures positive frequency. You have to put them together if you want to have a full picture. But this is just like what I had here. It's a little bit different because it's not symmetric, okay? But there is the Kondo resonance, the Kondo peak. This system has the so-called side bands at epsilon d and epsilon d plus u, but it does not have the Kondo peak. Why? Because the Kondo temperature of this compound is too small. And at the temperature where it's measured, you cannot see it. Because as the temperature is raised, this guy increases and kills the condo resonance. So in that case, you don't see it. And here are condo resonances. So this is low energies only. So this is not actually this sideband. This is spin orbit split level. You see the condo resonance. This is just photo emission, so just negative frequency with respect to the Fermi energy. You see different widths for different compounds because they have different condo temperatures. So this is a very large condo temperature system, has a very wide resonance, but as you move down the list, condo temperature goes down and the condo resonance goes away. Okay, so this can be measured actually directly in photo emission or inverse photo emission. So sometimes also called BIS. Okay. And these are the, well, I put 4 here, but I think I have 5 here, okay? So the width of the condo resonance is pinned to the Fermi level. It's very important for the physics that's coming in the next lectures. So this is pinned. Why is it pinned to the Fermi level? Because this is the condo effect. The condo effect happens at the Fermi level. Remember that the condo temperature had the density of states of the conduction electrons at the Fermi level. It's a low energy thing. Okay, so that's why if you move the Fermi level somehow by putting more electrons, the condo resonance follows the Fermi level. It's a Fermi level or Fermi energy phenomenon. So it's pinned to the Fermi level. Very important. The width of the resonance is Tk at t equal to 0, but as you increase the temperature, where is the width? It's here. This guy becomes big, and the width becomes larger. Okay? At t equal to 0, it decreases rapidly with increasing U. Why? Because it's the condo temperature. If you increase U, the condo temperature decreases, and it decreases. The height of the condo resonance is unaffected by interactions, which is this result. The quasi-particle weight, Z, causes the renormalization of the condo resonance width. The width has a Z in it. And it gives also the spectral weight, the integral over the condo resonance. And it's intimately related to Tk, therefore, if you increase U, it decreases, okay? Okay, so let me announce next lectures, I'm going to sort of use a method for calculation for a lattice, let's say for the condo, the Hubbard model, but it relies on this picture for the condo problem. So I'm going to use this stuff in the reasoning that comes afterwards, right? With some modifications here and there, but that's why I needed this part. And it comes from Fermi liquid theory because it's a low energy theory for fermions. Okay, that's it. I'll end here.
Questions?
Thank you for this nice talk. When you expand this gamma, in you mentioned that the first term is constant and the second is 0. Why is 0 the second and why is the constant the first?
Yeah, both the 0 order and the first order terms are 0. So the expansion starts at second order.
But why?
Which is why, I forgot to mention this, which is why sometimes I never even put this in the theory, because this is small. At low energy, this is very small. So most cases, it can be neglected, unless you start to raise the temperature. Okay, does that answer your question? Okay.
I guess he's asking for some intuition. Why it's 0? Why it's
Ask Landau. No, there are, okay. Let's start with the linear part, okay? What Landau theory hypothesizes is that the low energy excitations are long-lived. They have a long lifetime. the inverse of the imaginary part of the self-energy gives you the lifetime of the quasi-particle. So if that's large, it's not going to live long. So it has to live long, and it has to live long enough for you to define the quasi-particle. In other words, it has to be much smaller than this part, which is why it has to start at square. Now, many attempts at breaking down Fermi liquid theory come from us not assuming this, that the linear part is there. Actually, the famous high-TC superconductors, the resistivity is a linear temperature function of the temperature. It's linear in T. The resistivity is a measure of this guy, the imaginary part, well, with a couple of modifications. But it's essentially a measure of this imaginary part. So most metals, the resistivity at low temperatures is T squared. That's Fermi liquid. So if you get linear, that's Fermi liquid breaking down. That's what we would like to understand. High TC is like that. If you take, there are some compounds high TC where you measure a linear resistivity from, let's say, 20 Kelvin up to 1,000 Kelvin. It's a perfect straight line. A perfect, absolutely perfect straight line. Absolutely nobody knows how to understand this, how to explain this. This is the big mystery of the high TC superconductors. Why the resistivity is a linear function of temperature. Okay, so this is Fermi liquid breaking down. Now, the zero part, okay, in the context of the usual Fermi liquid theory of Landau of metals, the constant part, if it was there, it would break down a theorem called Luttinger theorem, which can be proved in perturbation theory. It essentially says that if the Fermi surface is a square, is a sphere, like in helium-3, it does not get renormalized by interactions. In other words, the Fermi sphere has a radius which is kf, the Fermi wave vector. So Luttinger theorem tells you that no matter what u is, kf is unrenormalized. So the size of the Fermi, the volume of the Fermi surface does not change. Okay, and that is guaranteed if you impose that the imaginary part is precisely zero at zero frequency. Okay, so in the context of extended system, that's the reason. In the context of this system here, it also would mean that you don't have quasi-particles. So you have to start at square. Okay? Otherwise, the quasi-particle decays. It's not well defined at low frequency. Okay? So that's an intuitive explanation. I hope it is intuitive.
I have a very, naive question, I guess. And you started talking about, you wrote down a Hamiltonian which is quantum. My question is there any hope that we could have some classical model to understand the insulators? Or at least, I know it's a very low temperature phenomenon and so on, need conditions and electrons, but is there any model that can give us some intuition about, no, classical?
I don't think so. I don't think so. Everything that's interesting in this area is quantum. Of course, there is a classical regime at very, very, very high temperatures. But nothing interesting happens, as far as I remember, in the classical regime, which is usually extremely high temperatures, right? It's like 10 to the 4th Kelvin. The metal melts down. But even in situations where you could have very large temperatures, if you go into the classical regime, it's going to be, as far as I know, there's nothing very interesting going on there. So you have to be quantum.
Okay, let's thank Eduardo again. Please, people who are scheduled to present their posters this week could hang them out now during the coffee break, okay? Or could put them there later in the afternoon. And remember that you have